Welcome to today's explainer, where we are going to unpack the fundamental building block of data structures in C programming, arrays. Seriously, if you've ever found yourself writing 10 different, slightly named variables for 10 similar pieces of data, you already know there has to be a better way. Well, today, we're going to master exactly what that better way is. Here's a quick look at our roadmap for today. We'll cover array fundamentals, initializing array elements, using symbolic constants, practical applications, character arrays as strings, and then we'll wrap up with a final recap of the key rules. All right, let's jump right into section 1, array fundamentals and memory. So what exactly is an array? The absolutely crucial point here is that an array is a static collection of variables placed sequentially or contiguously right there in memory. This means every single element in that array shares the exact same name and the exact same data type. You can think of it kind of like a perfectly organized row of lockers in a hallway, where every single locker holds the exact same type of item. To put that into perspective, think about a standard 12-element array named C. The very first position isn't 1, it starts at position 0. That is our 0th element. This is a massive, fundamental rule in C known as zero indexing. When you want to access that very first item, you use the subscript 0 inside square brackets. And because we start at 0, if you have 12 elements, your highest index is actually 11. Honestly, forgetting this is probably one of the absolute quickest ways to introduce really frustrating bugs into your code. Moving on to section 2, initializing array elements. Okay, so you have your array, but how do you actually get initial data into those memory locations? You essentially have two main approaches here. The first method uses a standard for loop to iterate through and set each index to 0. And a quick pro tip, notice the use of the size t data type for the loop counter. That's an unsigned integer type highly recommended by the C standard specifically for array subscripts. Now, the second, and honestly much more direct method, uses a comma-separated initializer list tucked inside curly braces. This is super handy because it lets you populate the array with specific values right at the exact moment you define it. But as you start writing this code, you really have to watch out for a few instructor-emphasized pitfalls. Specifically, keep an eye out for Common Programming Error 6.1. If you just define an automatic local array and completely forget to initialize its elements, those memory locations aren't empty. They're going to contain random garbage values left over from whatever program used that memory last. Also, Error 6.2 warns us that if you cram more items into your curly braces than the array was built to hold, the compiler is going to hit you with a syntax error. Interestingly, though, if you provide fewer items than the array holds, C is actually pretty helpful and will automatically initialize all those remaining elements to 0 for you. Let's look at section 3, using symbolic constants. Imagine you're writing a massive program, and you hard-code the number 10 for your array size across 20 different loops. Now, what happens if your requirements suddenly change and you need 1,000 elements? You'd have to hunt down every single instance of the number 10 and change it manually. It's a total nightmare. Instead, using a symbolic constant, like #define size 10, makes your code infinitely more scalable and maintainable. You just update that one number in a single place at the very top of your file, and you're good to go. Let's step through exactly how this works under the hood. The C preprocessor is basically a distinct little tool that runs before the actual compiler ever touches your code. It scans your file for preprocessor directives. Those are the commands starting with a hashtag. When it finds your symbolic constant, it simply performs a literal find and replace, swapping the constant name out for the replacement text you gave it. Only after this text replacement is completely finished does the C compiler step in to actually compile your updated code. I want to highlight a major assignment saver right here. Remember that preprocessor directives are not standard C statements. So if you accidentally end a #define directive with a semicolon, the preprocessor will literally inject that semicolon everywhere the constant appears in your logic, causing massive, incredibly confusing syntax errors when you try to compile. Also, just as a general best practice, always use uppercase letters for your symbolic constants. That way, they instantly stand out from your regular lowercase variables. All right, moving into section 4, practical array applications. Here is a really clever technique for analyzing data. Let's say we are summarizing 40 student survey responses with ratings from 1 through 10. Instead of writing a massive wall of if or switch statements to count the votes, we just use an 11-element frequency array. The trick here is that we use the actual survey response value directly as the subscript index to seamlessly count occurrences. So if a student answers 7, We simply increment frequency 7. It's that easy. We totally ignore index 0 here, just to make our code cleaner and align perfectly with the 1 to 10 rating scale. But listen, there is a massive word of warning we need to discuss, highlighted perfectly in Error Prevention Tip 6.1. C does absolutely no array bounds checking at runtime. None. If your array has 10 elements and your code accidentally tries to write data to index 13, C will not stop you. It won't even gently warn you. Your program will quietly walk right off the end of the array, overwrite other memory locations, and either cause a spectacular crash or create a very severe security vulnerability. It is 100% your responsibility as the programmer to ensure your loop counters and indices never ever exceed the size of the array -1. But once you master indexing safely, your data processing capabilities become incredible. You can effortlessly generate visual histograms using nested loops, where an outer loop goes through the array and an inner loop prints asterisks based on the value. Or you can brilliantly summarize the results of a die rolled 6 million times. Seriously, instead of trying to use separate variables to track every single roll, a simple little array gracefully captures all that massive data into just 6 meat frequency counters. Up next is Section 5, Character Arrays as Strings. So in C, there actually isn't a separate dedicated string primitive data type like you might be used to if you've played around with Python or Java. Instead, a string is simply a one-dimensional array of characters. But there is one absolutely crucial difference you must remember. A string in a character array must always be terminated by a special null character. We represent this with a \0. This invisible marker is exactly how functions like printf know where your text actually stops in memory. Now you can initialize character arrays right off the bat with a string literal in double quotes, and the compiler is smart enough to add that null character for you automatically. But you really have to be careful when handling user input. When you're reading strings from a user with the scanf function, you should always use a field width in your conversion specifier. For example, using %19s for a 20-character array. Why 19? Because it leaves exactly one space safely reserved for that vital null terminator, physically preventing the user from typing a string that is too long, which saves your program from walking off the edge of the array and crashing. And that brings us to Section 6, our final recap and key rules. First off, keep in mind that arrays are the absolute perfect tool for statistical analysis. By iterating through an array, you can easily sum up the elements to calculate the mean. By sorting the array, finding the median is literally as simple as grabbing the middle index. And as we saw earlier with the survey example, tracking frequencies directly via array subscripts makes finding the mode, the most frequent number, an absolute breeze, just as long as you manage your loop bounds correctly. So let's summarize your core study checklist for your next assignment. 1. Always respect the 0th element. 0 indexing is the law of the land. 2. Police your own array bounds, because the C compiler definitely won't do it for you. 3. Keep semicolons strictly away from your preprocessor macros. And finally, 4. Always cap your character string arrays with a null terminator. Armed with these core memory concepts, strict syntax rules, and vital error prevention tips, you now have a highly structured, incredibly powerful tool for handling large data sets. So I want to leave you with this final thought. How will you leverage arrays to write cleaner, more efficient, and far more secure code in your next C programming challenge? Thanks so much for joining me on this explainer, and I'll catch you next time.